Alright, this is probably going to take a minute to get through. So this is the bridge that we talked about in class. So it has these members here. You can follow this around. Remember, it has a pin at point A, roller at point C. I apologize for how scrappy this picture looks. This is all from my notebook. So, but you can go back and look at your diagram that we did already. So we had 1,000 pounds here, 250 pounds here at point B, and 500 pounds, my zero didn't come through on the picture, at point E. Okay, it's 3 foot tall and 10 feet long that the structure fits inside. The first thing we have to do is look at static determinacy. So we're looking at this thing right here. So 2J equals M plus R, and we find that there are 5 joints, so 2 times 5 is 10, and there are 7 members. So 7, and then 3 reaction forces. We'll have 2 reaction forces at A, right here, and we'll have 1 reaction force right here at point C. So that means, I wrote it wrong. So 7 plus 3 is 10, so 10 equals 10, and I wrote it wrong in my notebook because I was already thinking about the next thing. The next thing we need to look at is the we can look at the reaction force in X at point A, and we know that the sum of the forces there has to equal 0. So the reaction force at 0 at RA in the X direction is 0. That's pretty hard. Now we're going to consider point A as our fixed point of rotation, and we have RCY holding it up, and 3 forces pressing down. And all of these have to equal 0 when we look at the moments. So we have 1,000 pounds here, 250 pounds here, 500 here, and then RCY presses up. So the sum of the moments has to be equal to 0. So the sum of the reaction forces has to equal 0. So that means the moment at RCY minus the moment, I should have put moments here in such a hurry. The moment from force D and force B and force C has to equal 0. So we plug in the moment formula here. This is the meaningful calculation here. So we have the reaction force times the distance minus the force D times its distance minus reaction for, or the force B at its distance, force C at its distance, and that should equal 0. So let's plug some numbers in. So the reaction force at point CY is 10 feet, 1,000 feet is 1,000 pounds is at 3 feet, 250 pounds is at 5 feet, 500 pounds is at 7 feet. And remember how we talked about when the reaction forces, or the force pressing down, is at a right angle to the distance. That's the one we're interested in. So we're just looking across the bottom part of the bridge. So when you do all the math here, so we multiply all of that and get a total of RCY times 10 equals 700 or 7,750, and you complete the algebra, and you get that the reaction force in the y direction is 775 pounds. So starting with this formula, we're looking at the sum of all of the forces in the y direction has to equal 0. So that means the reaction force at A, the reaction force at C, the force pressing down at D, the force pressing down at B, and the force pressing down at C have to equal 0. So we isolate RAY and plug in the numbers. So we get 1,000 plus 250 plus 500 minus 775. And I'm sorry for the bleed through, I used the wrong kind of pen. When you run all that through your calculator, you get 975, and that's pounds, and that's pressing down right here. Well, that's the reaction force holding up. Okay, so now if we look at point A right here, we will see that we have a couple of things going on. We have a reaction force in X and reaction force in Y. We know that X is 0 and up is 975 pounds. That means that the reaction force from ADY has to be equal and opposite to 975. So let's take a look at this. So now we do a little trig to find the force acting on point or member A to D, and we do a little bit of trig. We know that sine theta, theta being 45 degrees, is equal to ADY divided by AD, and we're solving for AD. So I did that backwards. That should be 80y, and this is 80. Oh man, I can't believe my terrible writing. But if you solve for the hypotenuse, you get a minus 975 divided by sine 45, and you get a total force on ADY of negative 1,378.86 pounds, and that means that it's in compression since it's negative. Remember, our rules say that if it's positive, it's in tension. If it's negative, it's in compression. Okay? To find this tension, or the forces acting from A to B, we know that the sum of the forces on AB have to be, or in the x direction, have to be the sum of RAX plus AB plus AD sine theta, and theta being 45 degrees. Okay. We know that RAX is 0, so that means that AB has to be AB plus AD sine theta have to be equal to 0. We isolate AB, and we end up with a negative AB is equal to AD sine theta, and we know that the actual force acting on AD is negative 1,378, and we multiply that times sine 45, and we get negative AB. The negatives will cancel, and lo and behold, AB is 975. Using a little bit of simple trig, we could have just said, well, if this side's 975 and this side is 45 degrees, and we know that the other forces acting here are 0, then we should know that this is 975 as well. Okay, and we know that this is in tension because the final result is positive. Now we're going to jump over to the other side where we have point C, and we know that we have a reaction force of 775 pressing up, and a equal and opposite force from EC in the y direction of minus 775. So we can follow this same strategy to find the value for member CE. And we do a little bit of trig, so CEY over CE. To solve for CE, it's going to be CEY divided by sine theta. And that means CE is negative 975 from right here, divided by sine 45, and you get a negative 1,096.02 pounds. And that is the compression happening between C and E. So the next thing we're going to look at is a little confusing. No, we're not. No, it's not. We're looking at from CB. So we're looking from this point to this point. And similar to last time, short answer is if this is 775 and this is a 45 degree angle, and CB is the equivalent to the component of the triangle CEX, because there's no reaction force in the x direction, right? So that should be 775 as well, because it's connected to the center point here. But just to make sure, we're going to go through the algebra. So here we go. That means the sum of forces in Fx has to be equal 0, and we know that CB plus the adjacent component of CE is going to be equal to 0, and then you have a negative value for CE, and that's going to be equal to a negative value for CB, so the negatives are going to cancel out. When you do this math, you still get 775, and there is your tension. CB is in tension. And we kind of know across the bottom it's probably going to be in tension. Okay? So starting from here, we have to look at the tensions in relationship to point E, and what's going on in X and what's going on in Y. So I think I solved X first. Let's go look at the notes. Nope, started with Y. So if you think about what's happening at Y, we have EBY pulling down, the force at point E pulling down, and RCY, which is equivalent to CEY pushing up. Okay, let's go look at this diagram again. Okay, so if you look at this, we have a Y component coming from EB going down. We have the load pulling down, and we have this force CE in the Y direction pushing up. Okay, so if we add all of those forces together, we have the sum of FE plus RCY or CEY, and the plus EBY should equal 0. And if we replace the numbers with the ones going down as negative and the one going up as positive, we have minus 500 plus 775 minus whatever EBY is. We can replace EBY using trig with EB sine theta, and we can solve these down to 275 because 775 minus 500 is 275. So the sum of the forces in y is going to be equal to 275 minus EB sine theta, and that's going to be 0. So we can rearrange this and move EB sine theta to the other side, so that means everything's going to be positive. And we do the trig here, 275 divided by sine of 56.31 degrees, and we get a value of 330.5 pounds. It's positive, so that is in tension. So what we're saying here is this member is under tension right now, based on how these forces are lining up. The next thing we need to do is look at the forces in X, and we need to recognize that from the perspective of point E, the X component of EB is pulling to the left, the X component of C to B is pulling to the left, and the X component, or the member ED, is also pulling to the left. So everything is going the same direction, so we can just put all of those in as a positive value. So I go through a little bit of trig here, showing how we can replace EBX with a trig function, and that's the only thing we don't know. We know ED, and we don't know ED. We do know EB, and we found that earlier. And so we can find that X component from EB, and we know that CBX is also 775 because of what we know from the bottom of the bridge. So we can replace these with numbers and get ED down to being a value of negative 958.32 pounds, and that is in compression. So if we redraw that, we end up with this point where it has a compression line here of 1,092 pounds. We have tension here at 330 pounds, and we have compression here at 958.32 pounds. Okay, so now we're going to look at the forces happening at the point D, and the only thing we have left is DB. And we know what's happening in DBX, and we know what's happening in DBY. And I solved this first with by using the sum of the forces in X, and I got this value, but then I look back at the Project Lead the Way notes, and they do it from Y, so I cross this out, and we're going to do this in Y. So if you look at the forces in Y, we have DAY, which is the Y component of the member DA, and that is the response to the reaction force holding it up, and that's going to be a positive value. The force at point D is pulling down, and we know that DBY is also pulling down, and DBY is equivalent to DB times the sine of theta. So we can replace these two with their numbers, so we have 978 pushing up, and we have 1,000 pounds pulling down, so we have negative 25 minus dB sine theta, or sine 56.31, and we can rearrange this to solve for dB, and that means that one of these has to be negative and one has to be positive, so dB is going to be minus 25 divided by sine of 56.31 degrees. And that leaves us with a compression. It's compression because it's negative. A compression of 30.046 pounds. So the next thing we would do is, as you've been doing this, you should have been labeling your bridge all the way. So we should have ended up with this diagram where we have the reaction force here, 975. The reaction force here, 775. We have a compression in this member, 1096. Compression in this member, 958. Compression in this member, 1378. We have a force going down with 1,000 pounds, a force going down with 1,000 pounds. And then we have tension here, 975, and we have tension here, 775, and then we have compression on this member at 30 pounds, and we have tension in this member at 330 pounds. This was a little bit of a surprise because we thought we would be seeing this, but we also have this force which is causing this to push down even more, so it's stretching these between B and E. Okay, again, the ones I give you to solve will not be near this complicated, but this has been a good exploration in how to solve these forces.